All right, so we're going to work on this three-wire circuit here. And what we're going to be looking for is the load across, or the voltage drop across load 1 here. The voltage drop across load 2 when the neutral breaks here. And this is going to show the effects of what can take place when you don't balance your loads between line 1 in neutral and line 2 in neutral. So whenever you're looking to solve a broken neutral type question, what we need to do is first we need to figure out what the resistive value of load 1 is and what the resistive value of load 2 is. That's our goal here. And the only way that we can do that with the information given is to be able to solve this particular question with the neutral intact. So these current values here assume that the neutral is together. So that would be presented in the question, in this particular question. It would clarify that the current value is 22 amps and 7 amps is when the neutral is actually intact. So we're going to assume the neutral is not broken at this point. So we have our current values going through load 1 and load 2. And now we can figure out, because 22 amps is flowing through our load, and we know the direction, we know that 22 amps must be flowing through clockwise through your conductors. And so we get 22 amps going through that conductor because these are in series here. They share one path. And we have 7 amps going through line 2. All right, so this is a very unbalanced circuit, and we know what the current would be going through the neutral. It would have to make up the difference between line 1 and line 2. So 22 amps is leaving our source and going to the load, and 7 amps is leaving the load going back to the source. So we need to make up that difference going back to the source so that our current leaving the source matches what's coming back to it. So 22 minus 7 is going to be that difference. And that is 15 amps flowing through our neutral. All right, so now that we have our resistance and our current, we can figure out what the voltage is going to be through each of those conductors and what the voltage drop will be in that particular circuit. So here, that'll be 22 amps times 2, which is 44 volts. Line 2 times 7 is 14 volt drop, and through the neutral will be a 15 volt drop. All right, so if we got a 44, well, now we got to figure out what is the remaining voltage drop on our load. So we're going to solve each of these loops individually. So we have this 120 volt loop, and we have this 120 volt loop here. Now our current going through this loop here, through our load and back through the neutral, and then back to 120 volts, is going to be 22 amps leaving the source. And a 44 volt drop. So we have 120, we start with 120 volts, and we have to subtract that 44 volt drop on our conductor. So we're down to 76 volts. Also, because our current direction through our loop, which is dictated by our current direction going through line 1 here, this direction here, because our current direction is flowing in the same direction as our neutral, that 15 volts is going to be a drop as well. So we're actually losing another 15 volts. So we're only got 61 volts left at our load. So this clearly is not a very well designed circuit if we only got 61 volts. In fact, it's not going to be anywhere near the requirements as per the Canadian Electrical Code, which only allows you 3% drop in any branch circuit. So we've dropped almost 50%, which is way beyond. Either way, this is a make-believe question just to help us calculate and understand the effects of an unbalanced circuit. So we have 61 volts through load 1. So let's figure out load 2. Our loop direction from our neutral back to line 2 is going to be the same, but this time our loop direction is actually opposing our current flow through the neutral at this point here. So our loop direction is going this way, then around, which opposes our direction here. So this 15 volts now on our neutral is actually going to be a rise. So we actually gain 15 volts. So 120 plus 15 gives us 130 volts, 135 volts. Subtracting 14 volts lost through line 2. So we end up with 121 volts across load 2. All right. So now we know our voltage drop across our loads. We can figure out what our resistance is going to be of those loads. And that's important to find because our resistive values do not change even after the neutral breaks. Those resistive values in load 1 and load 2 are fixed. And so even when our neutral breaks, it's not going to change. Just like our source voltage isn't going to change as well. Either way, we have 61 volts at load 1 and 22 amps. So we'll divide 22 into 61 and we get 2.77 ohms. On load 2, we have 121 volts divided by 7, which gives us 17.3 ohms. So that's our resistive values of each of those loads. Okay, so now at this point, our neutral breaks, and the entire circuit is going to change. The only thing remaining the same, again, is our source and our resistance of those particular loads. So we'll get rid of everything else. We have our break in that neutral now. Our currents are going to change. Cross that out. Okay. So because we lose our neutral, we can actually get rid of the neutral altogether. Let's try to do that here. If it's going to work. Nope. Okay, so our neutral breaks. Now we can disregard it completely. So now our 120 volts and 120 volts across line 1 and line 2 is actually going to be simply 240 volts. So we can get rid of that 120 now. We no longer have the neutral, we no longer have the access to the 120 volts on each side of our source. Alright, so this is what our circuit's going to look like. And you'll notice it's a simple series circuit with still our 2 ohm resistors within the conductors themselves. So what we have here is we got our total voltage, which is 240 volts. Our total resistance we can figure out by just adding all the resistors together. So we can take the 17.3, add the 2 plus 2 for our conductors, as well as the load 1, which is 2.77, which equals 24.1 ohms. Alright, so because we know our total voltage, we know our total resistance, we can figure out now our total current using Ohm's law. which is going to be approximately 10. So we get 240 divided by, so we end up with 9.98 amps. All right, so that 9.98 is going to be going through each resistor. 9.98. 9.98 amps through there, 9.98 amps through load 2, and 9.98 amps through line 2. Now we can figure out what our voltage drops are using Ohm's law. So 9.98 times 2 is going to give us our voltage drop through the conductor. So we'll call that 20 volts drop there, 20 volt drop there. All right, and then we have through load 1 is 9.98 times 2.77 gives us only 27.6 volts. And then 17.3 times 9.98 gives me 173 volts across load 2. So we have an extraordinary amount of voltage across load 2, where we should only have 120 volts. So if we had like a light bulb there and our neutral broke, then that light bulb would be probably destroyed. And along load 2, if we had a light bulb there, we're only getting 27.6 volts, which would make that incandescent light bulb extremely dim, if on at all. All right, so those are our voltage drops across the conductors and our loads. Now the last thing we'd want to do is figure out what our drop across the neutral would be. So let's bring back our neutral. All right, the one thing we could disregard is our the resistance. Because there's a break in the neutral, there's not going to be current actually flowing in there, but there will be a potential difference on either side of that particular break. So we're looking for the voltage drop or the potential difference on either side of that break. If you were to touch one side and the other side, what voltage would you experience? Okay, so the way that we can do that is we know that we have our 120 volts between our broken neutral and line 1. That's going to be our source. And we know that all the voltage drops need to equal what our source is going to end the same amount as our source. So 120 needs to equal 20 volts, 27.6 volts, and whatever the voltage drop on the neutral is going to be. So we can call that Vn. Therefore, if we just rearrange the formula, we'd have 120 minus 20 minus 27.6, which is going to give us, I want to make sure I get this right, 72.4 volts across our neutral. So that is what we're going to see right there. Because our voltage drop here, and our voltage drop here, and our voltage drop here need to equal 120 volts. Also, We could figure it out tracing our circuit the other way as well. Let me just show that real quick. Okay, so if we were to trace like this loop here, we still have 120 volts. Our voltage drop here, our voltage drop here, and our voltage drop here. Well, let's take a look here. So the difference between the 120 volts and 173 volts and 20 volts. So if we have well, if we added up 173 plus 20, that would give us 193. And now the difference between 193 and 120 is also going to be 73 volts. So no matter what way you trace it, the difference between our voltage drops and our source voltage is still going to be 73. So 73 volts across the neutral would be our answer for that particular question.